this presentation about the transport of heat by water systems. Transporting heat with water instead of air allows to use much smaller pipe diameters because of the much higher specific heat and density of water compared to air. In this lecture, you are going to learn about these water networks and, most important, about the surface areas needed. Let's start with the heat conversion system, which may be located differently depending on the type of natural resource used. In general, systems using combustible resources like gas, oil or biogas will be placed on the roof in such a way that in case of explosion, the damage to the building is limited. It is sometimes possible to place it in the basement or somewhere else in the building, but it must be then placed in a special explosion-proof technical room. Electrical boilers and heat pumps can be more safely placed in a basement. Especially, a ground source heat pump will be placed close to the ground. The same happens when an aquifer thermal storage system, an ATES, is used. When geothermal district heating is used, or any other kind of district heating, the energy conversion takes place elsewhere in the neighborhood and there is only a heat exchanger, generally placed close to the street level, that is plugged into the district heating network. Exactly as with air systems, there is a whole network of pipes bringing the hot water and its energy from the central heat conversion system that we described in previous slide to each room or space in the building that needs to be heated. In standardized term, the heat conversion system is called the generator. The radiators or floor heating are called the emitter systems. And the water pipes, including all valves and pumps, are called the hydronic system. We don't show the pumps and valves here. We saw in another lecture that these pipes are very small, no more than a few centimeters diameter, so spatially that is not such a big deal and the architect will not mind too much. The pipes can be visible or worked out in the walls and the floors or ceilings. In that case, flexible pipes may be used. Of course, the central pipe is larger than the pipes to the room, but diameters remain very limited. Such a network, as in the figure, is called a one-pipe system and is old-fashioned and should be avoided as it leads to a decrease of temperature at each radiator. Look at the first radiator. The hot water cools down in the radiator and is re-injected in the warm pipe, which causes a temperature decrease in the main pipe. The last radiator gets water that is quite cold, by which the heating power will be very limited. This must be compensated by installing larger radiators. The further from the generator, the bigger the radiators. Additionally, such a system is difficult to control, so this configuration should be avoided. So, in an energy-efficient heating network, a so-called two-pipe system, the radiators should be placed in parallel, like that. There is a supply pipe in red and a return pipe in purple. In fact, they are connected to each other in a closed loop. This way, all radiators get the same temperature levels and can deliver the same quantity of heat. Even more branches are possible, like that. In the case of a building with 5 floors, we would have 5 main branches. I show now only 2 of them. This last configuration is very similar and is often used in combination with flexible pipes like in floor heating. There are then 2 headers. The red one is a distributor, the purple one is a collector. Finally, just like there is a fan in an air handling unit to push the air through the building and to compensate for pressure drop in ducts, we need pumps in the water system to push the water through, overcoming pressure drop and height differences, especially when the generator is placed in the basement. Generally, the pump is placed at the return side. You see here one of the radiators in the hydronic network of the building I am working in, with its supply and return pipes and the connection between the pipes and the radiator. On the right, you see the header of a floor heating system with distributor and collector. In general, the velocity of water in pipes should be limited to 1.2 meters per second to avoid noise and pressure losses. In another course and during week 1, you learned how to estimate the heating load of a complete building as the sum of transmission, ventilation and infiltration, solar gains and internal heat gains. Let's take again the same building as previously and imagine you have calculated the needed heating capacity, which is the maximum nominal load during cold weather. Imagine this total heating load is 600 kilowatt. There are 5 floors. Imagine there are 16 rooms per floor and they all need the same quantity of heat and we neglect the corridors. We therefore need to bring 600 divided by 5 divided by 16 is 7.5 kilowatt per room. How large should the radiators be? Now, let's look at the energy delivered by emitters and study it on the example of a radiator. It would be exactly the same for floor heating. Let's call the temperature of the water entering the radiator at the supply side Ts and the temperature of the water leaving the radiator at the return side Tr. You see them on the picture. We will take as example Ts equals 80 degrees Celsius and Tr equals 60 degrees Celsius. This radiator is nothing else than a heat exchanger, exchanging the heat contained in the hot supply water to the room air Ti, which is therefore heated, while the water is cooled down to Tr. The water in the radiator loses mCp Tr minus Ts, which is given to the indoor air. So, the heat delivered by the water in the radiator is Q is mCp times the temperature difference between the water coming into the radiator at the supply side, Ts, and the water leaving the radiator at the return side, Tr. In this example, we know that Q room heating is 7500 watt and we know the temperatures, so we can easily estimate the needed mass flow rate M, which is, by the way, controlled by the valve mounted on the radiator at the supply side. In our case, it is 0.09 kg per second. We can then size the pipe. The volume flow rate, M, divided by rho, the density of water, 1000 kg per cubic meter. So the volume flow rate is 0.09 divided by 1000, which is 9 times 10 to the power of minus 5 meter per second. Divided by the maximum velocity of 1.2 meter per second, this delivers a cross-sectional area of 7.5 10 to minus 5, leading to a radius of less than 5 millimeter, a diameter of less than 1 centimeter. More interesting is to remember that this heat is delivered to the room air through the surface area of the radiator according to this second equation, telling us that the heat exchange between a surface at a certain temperature and surrounding air is the temperature difference between the surface and the air times the surface area times a heat transfer coefficient alpha, representing convection and radiation heat transfer. The surface of the radiator has not the same temperature everywhere. It is 80 at the start and 60 at the end. It is possible to show that this mean is not exactly the arithmetic one, but that it can better be calculated using the logarithmic mean temperature LMTD as defined below on the slide and explained in a presentation on heat exchangers. Please also note that alpha is the convection and radiation coefficient depending on air velocity and design of the radiator, and A is the area of the radiator. If you know the temperature levels T supply and T return and the quantity of heat to be exchanged, you can then relatively easily estimate the needed heat exchanger area the area of the emitter, therefore, by using the law of conservation of energy, by which the results of equation 1 should be equal to the results of equation 2, leading to the formula below. The surface area, A, determines the size of the emitter, a radiator in our case, and therefore its costs. If we take again our example with a heating load of 7500 watt and supply and return temperatures of 80 and 60 degrees, this leads to a LMTD of 49.3, leading to a surface area of 20 square meter. This seems big, but the power of 7.5 kilowatt corresponds to a large room of about 125 square meter. In such a large room, one could place 8 radiators of 2.5 meter by 1, for example. As we will see in next slide, there are also lots of ways to increase the effective surface area of the radiator without increasing its size too much. Producers of radiators have generally done all these calculations for you, and you will just find product descriptions describing the size of the radiator and for which maximum heating capacity it is suitable. We described 2 slides ago that the heat transfer coefficient alpha consists of a convective and a radiative part. When it comes to products on the market, it is very confusing that producers sometimes categorize their emitters into radiant heating or convective heating. In fact, all products always have both components according to the laws of physics. In some cases, the emitter has just one flat plate, like this one. In other cases, the plate is corrugated, like on the radiator above and on this picture. Additional plates are added, increasing this way the effective heat transfer surface for convection. So, in general, we can rewrite the heat transfer equation like that, taking into account the outer radiative surface A and the surface for convection AC. The radiative share can then be calculated easily. In general, if the radiative share is higher than 50 to 60%, we will speak about radiant heating. The flat radiator on the picture is such one. If the radiative share is lower than 50%, we will call it convective heating. Old-fashioned radiators have in general a radiative share of 20 to 30%, but keep in mind that both radiative and convective heat transfer are always there. I also remind you of what you've learned in the course Health and Comfort in Buildings, being that the temperature of the surface is very important for the comfort. In this lecture, we looked at the location of heat generators and then studied hydronic networks, which are the water ducts distributing the hot heating water to the local emitters, radiators or flue heating, for instance. We saw that a good hydronic design with radiators in parallel is recommended. We also discovered that the diameter of water pipes is really small, and we described the way to calculate the size of the radiators needed to heat rooms. Thank you very much for listening.